Hi everyone, welcome to another video for Research Design and Analysis. This is our second in the series of videos on models with multiple categorical predictors. We're building off of the first video to talk about multivariable regression in general. So we haven't gotten to building in categorical predictors yet, but we're talking about some of the issues where we have multiple variables in the same regression model. So we're going to really build on the ideas from the previous video to drill down on what it means to control for another variable and how do we calculate an estimate of a slope when we have multiple variables in the same model. So as a reminder, in this example, we're using this hypothetical data set of students' ages, heights, and weights, and we're going to be looking at predicting weight on the y-axis as a function of height and age as our two different x variables. And we said that although in general students' weight increases as they get taller and it also increases as they get older, the issue that we have is a collinearity, right, or shared variance between our two x variables, because students also get taller as they get older. So how do we actually handle the fact that weight is increasing due to age, height is increasing due to age, and we have this variance shared between three different variables? So as you might recall, we showed the regression equation last time, but here's a statistical output from R that shows us these individual estimates. Right, we said that we had an intercept of negative 141.22. So that's the estimated weight for someone who is 0 inches tall, right, and 0 years old. So it's not a very meaningful intercept, right, because obviously that's not a real person, but it is useful as kind of an anchor point for our regression line. More critically in this example is the effect of height, right, where we got a slope of about 3.6. So for every 1 inch taller you are, we expect you to be about 3.6 pounds heavier, controlling for your age. And then there was also the effect of age, which was 1.28. So for every 1 year older you are, we expect you to be about 1.28 pounds heavier, controlling for your height, right? So we really want to think then about what does it mean to control for age when we're looking at height and control for height when we're looking at the effect of age. And as you might recall from the previous video, we have to exclude their shared variance in the calculation of these estimates. But then once we do, we can not only generate estimates for what these coefficients are, but we can conduct meaningful hypothesis tests to say, above and beyond age, is there a statistically significant effect of height? And above and beyond height, is there a statistically significant effect of age? So let's again look at this relationship in a slightly different way. So rather than that three-dimensional scatter plot, here's two-dimensional scatter plots where we're looking at weight as a function of height and we're looking at weight as a function of age, right? And again, you can see that there are strong positive relationships in both of these bivariate plots. But the tricky thing is, right, is that not only are height and age and weight related, but height and age are also related to each other. So what we need to do is remove the shared variance due to age in order to get a fair assessment of the effect of height on weight. So right here's the relationship between height and age. Here's the relationship between weight and age. So the part of height that is explained by age, right, we're capturing over here in the shared variance of these two circles. But the other way that we can represent that is with a regression line, right? This line represents the part of height that is explained by age. Similarly, right, weight and its relationship to age are represented by this area of overlap in our two circles, but it's also captured by this regression line, right? This is the part of weight that is explained by your age. So if I want to get the part of height that's independent of age, and I want to get the part of weight that is independent of age, what I need to do is get the residuals, right? I need to get what's left over in your height after accounting for your age. So we're going to break the parts of height and weight up into the parts that are independent of age, so that we can then use those independent residuals in our regression model. So we're ultimately, computationally going to have the computer do this, but what we are conceptually doing, right, is making a new variable that's no longer height in its raw units, but it's the residuals of height. Sorry, height's up here. So it's no longer height in its raw units, but it's going to be the residuals of height that we're taking. And similarly, it's no longer weight in its raw units, but it's the residuals of weight that we're taking. Right? So we're going to take these errors out and make them a new dependent variable. So we can plot those against each other here. So now if I want to see the relationship between weight and height controlling for age, I have my weight residuals here. So if you were at 0, you were right on the regression line in the previous graph because you had an error of 0. If you're above 0, then you were above the regression line, right? So you were heavier than we predicted for your age. So if you're heavy for your age, you're going to be higher on the y-axis. And similarly, if you were below 0, that means you were below the regression line. So that means you are light for your age on the y-axis. On the x-axis, we also have residuals, right? So 0 here would be somebody who was on the regression line in this plot up above. So that means then if you were at 0, you were right on the regression line. You were exactly the height we predicted for your age. If you have a positive residual, then that means you were tall for your age. If you have a negative residual, then that means you were short for your age. So now that we've taken age out of both variables, we can fairly assess the relationship between weight and height controlling for age. And if we do that, you see that we're going to get an estimate of the slope, right? So if I actually analyze these two residuals regressed onto each other, I get that same slope that I had from the previous multivariable regression of 3.6, right? So after the variance due to age has been removed, for every inch taller you are, we expect you to get about 3.6 pounds heavier. Now, we can do the same thing looking at the relationship between weight and age, but now we're controlling for height in each one. So again, we are looking at the residuals of weight on the y-axis, and we're looking at the residuals of age on the x-axis. So now if you were at 0, that means you were right on the regression line between weight and height, meaning you were as heavy as we would predict you should be for your height. And on the x-axis, right, if you're at 0, that means you are as old as we would predict for your height. So if you have a positive deviate up here, that means you were heavy for your height. If you have a negative deviate down here, that means you were light for your height. Okay, and then if you have a positive deviate on the x-axis, that means you were old for your height. And if you have a negative deviate on the x-axis, that means you were young for your height. If we then regress these two sets of residuals onto each other, we end up with a slope of 1.278, which you might remember was the effect of age in the multivariable regression, because now this is the effect of age once the variability of height has been removed. And although, in the sample again, it's a positive relationship, it's not statistically different from 0. So in contrast to the effect of height, where we said, okay, this is a strong positive relationship. For every 1 pound heavier you are, we expect your weight to go up by 3.6 pounds. Or sorry, for every 1 inch taller you are, we expect your weight to go up by 3.6 pounds, and that is statistically different from 0. When we look at the effect of age controlling for height, after that variance due to height has been removed, the effect of age, although positive, is not statistically different from 0. So regressing these residuals onto each other, gives us the same parameter estimates as in the multivariable model. So just to put all of that again onto the same screen, here's our original multivariable model, right, where we had an intercept of negative 141, height had a slope of 3.597, age had a slope of 1.278. Right? If we look at the individual regressions where we first took the variability due to age out, we had a slope of height of 3.597, right? So that matches. So this effect of height is the relationship between height and weight after the variability in age has been removed. Similarly, this slope for age of 2.784, right, that is the effect of age after the variability due to height has been removed. So in the multivariable regression equation, these slopes are conceptually the same as the slopes of simple regression equations once I've taken out the other variable. So after I've excluded the variance due to the other variable, I can get these slopes from these kind of individual regressions, because this is telling me about the effect of height after variance due to age has been removed and the effect of age after variance due to height has been removed. And again, you can refer back to our previous video where we talked about different ways of dealing with this shared variance, but this is based on the type 3 sums of squared errors calculation, where any shared variance gets removed from both predictors.